Today we're solving LeetCode 1877. Minimize maximum pair sum in an array. You're given an even-length array, and your task is to pair up all elements such that the largest pair sum is as small as possible. This problem is interesting because you're not minimizing the total sum. You're minimizing the worst-case outcome. And brute force pairing explodes combinatorially. This problem directly tests greedy reasoning, understanding of extremal pairing, ability to argue correctness, which interviewers care deeply about. By the end of this video, you won't just know what the solution is, you'll clearly understand why this greedy strategy is optimal. Let's reason before touching any code. We must form n divided by 2 pairs, and once the pairs are formed, the score of the solution is the maximum of all pair sums. So this is a classic minimize the maximum or bottleneck optimization problem. Why brute force fails? Trying all possible pairings. Number of combinations grows extremely fast. Becomes infeasible even for small n. So we need structure. Large numbers are dangerous, they dominate pair sums. Small numbers act as buffers. So if a large number must be paired, it should be paired with the smallest available number. Pairing large numbers together only increases the maximum, which is exactly what we want to avoid. This leads to the greedy insight. Pair the smallest element with the largest element. Pair the second smallest with the second largest. Continue inward. This spreads the values evenly and prevents extreme pair sums. We start with the list. Nums equals 3, 5, 2, 3. Step 1. Sort the list. After sorting in ascending order. 2, 3, 3, 5. Step 2. Initialize tracking variable. We will keep track of the maximum pair sum. Max underscore pair underscore sum equals 0. Step 3. Pair elements and calculate sums. We pair the smallest and largest numbers together. Iteration 1. Pair 2 and 5. Sum 2 plus 5 is equal to 7. Update. Max underscore pair underscore sum equals 7. Iteration 2. Pair 3 and 3. Sum 3 plus 3 is equal to 6. Update. Max underscore pair underscore sum equals max 7. 6 equals 7. Step 4. End of loop. All pairs have been processed. Final answer. The maximum pair sum is 7. Edge cases and failure scenarios. Minimum input size. When n equals 2, there is only one possible pair. The algorithm works trivially because no comparisons or choices are required. All values equal. Example, 4. Every possible pair sums to the same value. 4 plus 4 is equal to 8. Since all pair sums are identical, the maximum pair sum is 8, regardless of how pairs are formed. Highly skewed values. Example, 1, 1, 1, 100. By pairing the largest value, 100, with the smallest value, 1, the algorithm minimizes the impact of extreme values. This pairing strategy prevents any single pair from becoming unnecessarily large. Maximum constraints. The algorithm efficiently handles large inputs, including n equals 100,000. Because it relies on sorting followed by a single linear pass, it runs efficiently within time limits. Control flow. No special branching or edge case handling is required. The same logic applies cleanly to all valid inputs. Let's formalize the solution. Step 1. Sort the array. Sorting exposes the smallest and largest elements directly. Step 2. Use 2 pointers. Left smallest and used element. Right largest and used element. Step 3. Form a pair. Compute nums left plus nums right. Track the maximum of all such sums. Step 4. Move inward. Increment left. Decrement right. At every step, the largest remaining element is paired with the smallest possible partner. This minimizes its contribution to the maximum pair sum. Once a pair is formed, it never needs to be reconsidered. Explanation. Sorting enables controlled pairing. 2 pointers ensure each element is used exactly once. We track the worst pair, which defines the objective. This code is deterministic, safe for all edge cases. Optimal under given constraints. Time complexity. The algorithm first sorts the input array, which takes O of n log n time. After sorting, it performs a single two-pointer scan to form pairs and compute their sums. The scan runs in O of n time. Therefore, the overall time complexity is O of n log n. Space complexity. The algorithm uses only a constant amount of additional space for variables such as pointers and tracking the maximum sum. Ignoring the internal space used by the sorting algorithm, the extra space complexity is O of 1. This is optimal. Global ordering is necessary. Common mistakes. Pairing adjacent elements after sorting. Overcomplicating with DP or heaps. Failing to justify the greedy choice. What interviewers expect. To minimize the maximum pair sum, each largest element must be paired with the smallest available element. Follow-up questions. Can this be done without sorting? How would the solution change if the goal were different? The key idea is simple but powerful. Control extremes by pairing smallest with largest. This greedy invariant shows up in many interview problems. Master it. Practice similar problems,